So this lecture will actually be um, a footnote on some earlier lectures concerning the separation Femboy topological Femboy spaces. Okay, and I'm supposed to write this later. So Frischet, you have Hausdorff, normal Hausdorff, regular Hausdorff. Okay, so there are, aside topological invariants such as I suppose winding number, linking number, first, second countability, compactness, and things like that. There are these main categories we can sort of decompose a topological space into, or we can classify a certain topological space as. And these things that we can classify topological spaces as are what we call the separation axioms. So and the separation axioms are relatively simple actually. They're mainly, when you start or take an introduction to topology, there are mainly 4 separation axioms. And they fall under these T's with subscripts. So I suppose here now, what I'm going to say first, assume first, is let F, equipped with its topology, be a topological Femboy space. Which can be a B space, a topological B space. F, equipped with its topology, can be, so the first separation axiom, which we call T1, which is also called Frischet space, or Frischet space. If we have 2 points x, y, inside the space, and then some surrounding neighborhood, and then these neighborhoods intersect. So, yeah. So we have 2 points x and y, and then their neighborhoods intersect. If that's the case, your Femboy space, or your B space, or your topological Femboy space, is a Frischet space. So that's the first one. The second one, T2, is the most popular one, or the most well-known space. It is Hausdorff, or Hausdorff, either way. Hausdorff space. And Hausdorff means basically that, okay, so we have our points x, y, or we have 2 Femboys, x and y. The surrounding neighborhoods do not intersect. And just so you know, if I don't shade it, that means it's an open neighborhood. So it's an open set around x. So suppose we have just O over here, our O interval, and then we have a point x. A neighborhood would be something like an epsilon ball around x. So then this is a length epsilon. So that's a neighborhood. And so, okay, if we envision these guys as our O, or using our O interval, okay, so I'm gonna make a long, sort of long interval so you guys can see. Okay, so we have X, and we have Y. Let's say this is the origin, 0. Okay, so if it is a Frechet space, or Frechet space, it means that the intervals here intersect. So let's say that I want Y to contain 0. And assume that this is equal to this length, okay? Okay, now, let's say I want to construct the same epsilon ball of X, or, okay, actually, to make sure that 0 is actually part of this open interval, let's say that, let's extend it a bit, just a little bit, maybe to -1, where the femboy right below 0, and then, okay, oh no, let's make it an open interval, sorry, open set after all. Okay, and then this time, let's extend this interval such that it's something like the femboy right after 0, or the origin. Okay, so as you can see, now there is an intersection here. If I'm going to denote these two neighborhoods of femboys, mu1 and mu2, you will notice that mu1 intersection mu2 is precisely 0, or is set 0. Or mu1 intersection mu2 is the interval running from this femboy up to this femboy. So actually it's not, it's actually a set all alpha such that, okay, let's say that this this minimum of mu2 is, say, let's call it, yeah, the min of mu2, and then this is the maximum of mu1. Okay, I don't know if you guys can see that. So let's say this part here is the maximum of mu1, and this here is the maximum, the minimum of mu2. So now we classified the intersection between these guys to be the minimum, all alpha, or all femboys alpha, that are greater than the minimum of mu2, but less than the maximum of mu1. But if we don't quite specify it, or just say, oh well, they end at 0, let's say, well then their intersection would precisely just be 0. And so they would qualify, or this O interval, I believe our appearance, I think, behavior, dynamic, yeah, I believe dynamic, and then the P is the position, right? Not really, either way, our O cross P interval, if you recall from position theory. So if that's the case, if we have some intersection between these two neighborhoods, mu1 and mu2, this is a Frechet, a femboy Frechet space, or FF space, or it's T1, a T1 femboy space. Okay, so now let's consider that mu1 and mu2 have no intersection. So let's say now that the minimum of mu2 is greater than the maximum of mu1, or the converse. So let's now make the epsilon ball smaller. Okay? So this here is the minimum of mu2, still mu2 here. And then this is the maximum of, actually the supremum, sorry. This is the infimum, and this is the supremum. Supremum and infimum. This is the supremum of M1, and this is the infimum of mu2. And so we classify our neighborhood mu2 as the open I didn't specify this a while ago, but mu1, which is the neighborhood of x, of Femboy x, is the interval infimum of mu1, supremum of mu1. And then mu2, the neighborhood mu2, or the open neighborhood mu2, is the infimum of mu2. You need to specify infimum and the supremum so that your interval is bound. Okay, so, but notice that these two are not compact. Okay, so let's not talk about compactness for now. Or don't consider compactness just for now. We just want to say that, or we just want to discuss the separation axioms. Okay, so now notice that the intersection here is empty. Notice now that mu1 intersection mu2 is the empty set. So we have var nothing here, because notice that the supremum of mu1 is less than the infimum of mu2. It could be the converse, depends on how you want to phrase it. So that's that. Now we want to make a two-dimensional picture. We can make a two-dimensional picture here. So let's say we have our O cross P interval, or O cross P space. Our O cross P space. This is O and this is P. I believe it's the dynamic and then the appearance. Yeah, appearance. Dynamic and then appearance. So it's feminine and then like masculine stuff, and then we sort of map a point here onto our person or position state here onto our three main position state or main position state space. Okay, so alright. So let's say I have 2 points here. Let's say I have a point X specified by some, I don't know, 2 coordinates, or a pair of coordinates, or an ordered pair, but I'm not going to specify because that's not needed. Okay, and then let's say I have another point Y, or another femboy Y here, or position state. Now, what we want to do is construct an epsilon ball around these guys with, of course, radius epsilon. And let's say that the epsilon ball or the radius of the epsilon ball of X is bigger. So it's on good sort of extends outside of what we see right now, but it's big. Okay, so that's the epsilon ball of X. Now notice there's an intersection here between the epsilon ball of X and the epsilon ball of Y. Now you don't say epsilon circle because ball is a more general term. Because when we consider like a three-dimensional space, of course we can't just say circle. It has to be it's a sphere, right? So ball is a much more appropriate term. So if this is the case here, if we construct 2 epsilon balls between X and Y, such that the epsilon balls end up overlapping, and so they have an intersection, our O cross P interval is Freshet. And so, if it doesn't have, or if all epsilon balls are, it will be great. Or if you want your O cross P space to be Hausdorff, it needs to be that most of the epsilon balls, or if not all of the epsilon balls there, are, or rather the intersection of every epsilon ball that we can possibly construct over all points in your space. If the intersections between those epsilon balls are empty, then your space is most certainly Hausdorff. Very strong definition. I know it probably is a rare case, but if that's the case, wherein all possible epsilon balls you can construct, the intersection between those epsilon balls is empty, then your space is Hausdorff. and freshet space, let's talk about T3, T4 now. Now T3 and T4 don't really have names. We just call them T3 and T4. So I'm just gonna call it out here. So T3 space. I believe it's called a regular Hausdorff. Yeah, T3 is a regular Hausdorff. Regular Hausdorff. If, okay, so we have x and y again. Or just x. Alright, just x with its neighborhood, say it's mu1 again. And then we have another neighborhood over here of some unspecified point, mu2. But instead of a point inside it, we have a closed subset. So now I'm going to shade this to indicate that it's closed. Now, it's regular Hausdorff if we have this closed interval inside this interval, and then we have this neighborhood around the point, and they don't intersect. That's regular Hausdorff. It's called regular Hausdorff. And I suppose T4 is a normal Hausdorff. T4 normal Hausdorff. So T4 normal Hausdorff. This time replace x with a closed interval or closed subset. Keep mu2 in its closed interval. Now, if we have mu1 and mu2, and instead of points we have closed intervals inside them, then, and of course, mu2 and mu1 do not intersect, it's T4. So, okay, let's make a small recap. The separation axioms dictate, or at least try to segregate forms or different kinds of topological spaces, and thus, if we have a certain Femboy space, if we have a certain Femboy space F equipped with its topology, or a topological Femboy space, of course, it can be one of these four main types or four main separation axioms. Now there are other ones such as T4, T5, T3 1/2. T4 1/2, I believe, or T4 3/4, I believe, I forgot. But there are other types of Hausdorff spaces. For an introduction on the separation axioms and classifying spaces according to, well, their neighborhoods, this is a good place to start. So your topological Femboy space is freshet if we have neighborhoods around two Femboys that intersect. It is Hausdorff, just a Hausdorff, if those neighborhoods between the two Femboys do not intersect. It is regular Hausdorff if one of the Femboys is replaced with a closed subset that's entirely contained in the second neighborhood, and of course the two neighborhoods mu1 and mu2 do not intersect. And T4 or normal Hausdorff if mu1 and mu2 just contain closed intervals or closed subsets. So give a moment to sink in. Okay. Okay, so regular, normal, freshet, and Hausdorff space. There's actually a T0 there's actually a T0 space called the Minkowski space. Minkowski. I believe it's what's called Minkowski, I believe, or there's some other name for it. Yeah. Either way, there's a T0 space that we're not really going to talk about. Additional types of topological spaces we'll just discuss in a separate footnote. So these are the separation axioms. Great way of segregating your topological Femboy spaces. Okay, so now let's take a couple of facts. Now, in general, if your space is T4, it does not immediately imply that it's T3. Okay? Because here we're talking about a closed interval, and I can pick a point, right? I mean, if a person claims that, well, okay, let's have a T4 Femboy space, or FT space, or TF space, topological Femboy space. Okay. Let's assume a person, or let's say that a person assumes, or someone assumes that T4 here is T3. If we assume that T4 is T3, I mean, there's a reason why they're separate. There's a reason why they're not one type. Okay. T4 is not T3. It doesn't imply that it's T3. Okay? Because I can pick an X that is outside here. Or I can pick an X right here, such that mu1 would intersect mu2. And thus it wouldn't be a T4 space anymore. It would be T1. Frechet space. That's the thing about why T4 does not imply T3. Because I can pick a point that this neighborhood must follow or must be around, and if the point is sufficiently close to the second neighborhood, it would end up becoming a Frechet space, but with closed intervals. And likewise, T3 here does not imply T2. So if someone assumes, or if someone tries to claim that a regular Hausdorff space is also or can be a Hausdorff space, counter them by saying, oh well, the thing is, the reason why it's called Hausdorff is that one of the points here is a closed interval instead of a point. So it's more of a neighborhood of points here. So if I try to say, well, this is T2 here. Okay, let's assume that it is T2. So again, like with T4 implying T3, I can pick a point inside this closed subset. Notice how in a closed subset, the boundary is included. So I can pick a point here, and of course the entire interval must follow it. And if I pick the point sufficiently close, it will end up overlapping, or mu2 will end up overlapping with mu1, and it will become a Frechet space. So if you assume, or if someone assumes that T4 is T3 and T3 is T2, and applying the logic we just constructed by picking a point arbitrarily close to the other, or sufficiently close to the other interval, we would end up saying, well, T4 is T3, is T2, is T1, which is, of course, that's a contradiction. It's not true. There's a reason why we classify these guys separately. There's a reason why that's called regular. There's a reason why this is called normal. There's a reason why this is just called Hausdorff. And there's a reason why this is called Frechet. There's a reason why we classified them as T1, T2, T3, and T4. Okay? Now, the thing is, regularity and normality are not they're also intrinsic properties for these topological Femboy spaces. Because not only T3 and T4 are not the only spaces that are regular and normal respectively. In fact, T1 or Frechet is also regular, and T2 Hausdorff is also normal. So these two are sort of hold the same property, and then these two sort of hold the same property. Okay? Now I'm not going to provide the proof for that. Sort of consider that consider that as an exercise. to prove, in your spare time, try to prove that T3 spaces and T1 femboid spaces are regular, and T4 spaces and T2 spaces are normal spaces. Okay, prove that in your spare time. Okay, next thing I want to state is that normal spaces imply regular spaces, which implies Hausdorff spaces, which sort of implies Fresher spaces. But we're not following the logic that, oh, T4 is T3, T2 is T1. I'm just saying that this could be this in some cases, and this could be this in some cases, and this could be this in some cases. Well, of course, the case where this is when these two neighborhoods intersect. Of course, this would be this one if, of course, this would be a point, or there's a point here, all right? And then this close set or subset is the neighborhood on that point, or close neighborhood around that point. And of course, this implying this would be that, well, of course, these two are, one of these has a point, which it is a neighborhood of. Of course, the closed subsets. I'm referring to the closed subsets. Now, now how about metric spaces? Let's consider metric spaces or femboy metric spaces. So, we know that our O cross P space, the most common space that we use here in position here in femboy theory, it is a metric space. Essentially, a metric space is a space that can be mapped onto some other interval, onto R, essentially. So, a metric space is a space, or topological space, I believe, that has a metric, or a measure. So, we usually denote the measure as D, and this D maps 2 points, or 2 inputs, in that space, and then bring them, or actually it could be multiple inputs, and then it brings them to one output in R. So, our definition of a femboy metric space, in our study, is that it takes multiple femboys, right? It takes multiple femboys as inputs, and it outputs only one femboy. So, let's say that M is some femboy space. It is a metric space, or it is a measurable space, or metrizable space, if there is some D that maps M onto, well, actually, let's use a different thing so that you guys don't get confused with notation. Because I used M to denote a manifold, so I don't want to just, I will use M to denote a manifold. Because this footnote is early on in the lecture, or in the course. So, let's call it G. I know G is used for groups, but let's just assume that it's for our space here. Let G denote our space. Okay, so this measure here maps G tuples, arbitrary amount. You can just pick any, onto, I suppose, F1 space. So, like how a regular measure D, which we sometimes call distance, takes two inputs from R2, or actually R cross R. So it takes 2 points, and then maps them onto one number. So it takes some vector quantity expressed in 2 parts, and then it gives us a scalar quantity expressed in 1 part. The reason why it is denoted as D is because it's basically distance. The distance between actually 2 points. I believe it's R2 cross R2. Because it takes, I believe it's R2 cross R2. Because we have two pairs of points, and then we want to find the sort of distance between the 2 points, right? Or it could just be, well, R cross R, or R2 onto R. So, given one point, we want to find, or given one-dimensional points or two scalars, we want to find the sort of difference between the two, right? So it takes two inputs. Here, it's finding the distance between two pairs of points, right? In the same R2 space, of course. And now, for our metrizable space G, there is a measure D that maps multiple G tuples onto F. So it takes multiple two or more femboys and then maps onto F1. So it gives us some femboy. Actually, the neat thing about this is that it's actually something that's akin to linear combination, basically. So we can actually characterize this by a plus that maps G tuples onto F. F1. I don't need to write 1. Because notice how every femboy that we know, excuse me. Notice that every femboy that we know, or thus far, can be broken down, or at least femboys expressed as vector quantities can be broken down into principal stuff. So likewise, if we apply the inverse, now we have that multiple femboys can be combined into one femboy in F. So notice how, you guys know that F is the set that contains all possible femboys that we know, right? And G here is some, space. So notice how we can combine multiple position states, right? And express that sum, or linear combination, as a femboy in F. So that's this one example of our measure D. Okay? And if this exists on G, and we sort of just say, equip G with its measure D, this here is a metrizable space. It's metrizable. And the thing with metrizable spaces, is that there's a theorem in topology. I suggest you guys watch the lectures on topology by Bruno Zimmermann. I believe the book is written by James Monkers. So if you guys want to go deeper, you guys can check out the lectures that I watched, at least, when I got my education on this. So Bruno Zimmermann, James Monkers for the book, and yeah. So the theorem states that given some metrizable spaces, or a metric space, a metric space is normal. So it is somewhat like a metric space. Excuse me. A metric space is somewhat like T4 or T2. So it has closed subsets inside two non-intersecting sets or subsets, or open subsets, or it is Hausdorff or Hausdorff. So yeah, it can be T4, T2. That's the thing. So when given a metric space, it can fall either under T4 or T2 space. So yeah. So the thing is, when you want to say that a metric space is normal, you need to specify the parts that are open, because usually when we have a topological space, we don't assume anything yet. There's nothing we know about or there's nothing that we can classify on the topological space unless you say something or characterize that topological space by sort of specifying or identifying the open intervals, the closed intervals, and of course the open sets, closed sets, and if of course some closed sets, or if the open sets has closed sets, right, or closed sets, and of course it satisfies some stipulation under the separation axioms, make it fall under that certain of course T space, T1, T2, T3, T4. Now, I want to state now that normality or normal is a necessary trait for metrizability. So necessity for metrizability. Because notice how if our metric space is so now we want to state that if a space or a topological space is not normal, it cannot be a metric space. Now my logic on this is that the reason why it's metrizable, or that it's the reason why that it's metrizable because of being normal is that, well, of course we have that two inputs, right? Do not map or don't get confused. Notice how, okay, let's assume that a T1 space is metrizable. Now you may notice that, of course, the subsets now have intersections. That means the subsets have some element that is part of both of them, right? That's the definition of an intersection. But the thing is, when we want to map stuff, right, we want it to be distinct. We want there to be no points coming from two intervals or two subsets of that one thing. And so, if we assume that our metrizable space is T1, D would not exist. It's not a function. It's not a map or morphism or homeomorphism. Because notice that maps can be, one to many. One to many, but it cannot be many to one. It cannot be many to one correspondence. So because two subsets of the space contain one or more elements that are, or actually, let me rephrase that. Since our T1 space has elements that are contained in two intervals or two subsets, and so we map those two subsets, that means we have multiple elements that are mapped from the same subset onto, whatever the heck we want to. So it's essentially many to one, which is actually one to many. So that's a bit ambiguous and, of course, not a function anymore. That's the reason why whenever we construct piecewise functions, that's defined around the point, we make sure that the point is part of one part of the piecewise function, but not part of the second one. So when we specify the interval, so like less than, we do not use equal to, or less than equal to, on both sides, or on all of the piecewise functions around a point. Because it would mean that the interval would range, or the point would give multiple outputs, which is not good. And it would make it not a function. It would fail the horizontal line test, essentially, or I believe it's the vertical line test. So for all morphisms, I believe, the vertical and horizontal line test to determine functions still applies. It still applies, okay? So there's a reason why T1 cannot be metrizable. Okay. The reason why it's sort of, how I'd like to think about normal spaces is that, there's no ambiguity here. So we can cleanly map elements from this subset or this space, or subsets from this space, onto subsets of another space, or to another space, without without one input giving multiple outputs. Okay. So it's a metric space right there. All right. So I believe that's it. We're at 40 minutes right now. I believe we can still extend a bit just because these lemmas, but I feel like it's not necessary. So I'm gonna stop the lecture there. So just a recap. T1 space, if there's an intersection between two neighborhoods surrounding 2 points, 2 distinct points. T2 space, or T2 femboy space, if we have, 2 points now, T2 or Hausdorff femboy space. If there is 2 points, right, and then there are open intervals around the points that do not intersect. T3, if one of the points is replaced with a closed subset that's contained entirely inside the neighborhood. And T4, if both of the points are closed subsets contained in their respective neighborhoods that do not intersect. So, and yeah, T4 implies T3. Let me just sorry. Normal implies regular, implies Hausdorff, implies T2 or T1 space, but T4 does not imply T3, does not imply T2. And last thing, T3 and T1 spaces are regular, T4 and T2 spaces are normal spaces, and a metric space must be normal in order for it to be a metric space. So that's it for this footnote. I know this is quite a long footnote. I think footnotes are only like I think 13 minutes long, or maybe 20 minutes long. In fact, that's like the gross majority of the videos Femboy Physics makes. His videos are like, I believe, under 30 minutes long, and then my lectures are like more than an hour long already. So, apologies for that. In other news, I played Celeste, and it's a great game. I've heard that actually it's a bit scary because when I found out about the game, it was from a Discord server I'm part of, and they said that if you play the game, right, really makes you question your gender. People, I heard this, or so I'm told, people actually transition because of the game. And what I really love about the game is, well, of course, it's very hard platforming. It's very, very hard. It's very hard. It's frankly a very, very hard game. One of the hardest games I've ever played, aside, Doom on very hard modes. It's a very hard game. That's the thing. And very hard game. And what I really like also that really keeps me from rage deleting the game is that the protagonist, Madeline, is actually transgender. I'm like, whoa, that's so cool. It's like, maybe that's why people were transitioning because of the game, because they were convinced that this protagonist pushed through all her struggles, her anxiety and her depression and stuff like that. It's like, yeah. Now I know it's not. I know what I just said or what I just talked about is not at all connected to the lesson, but it's a small tidbit. I played Celeste, and it's a great game. It's a good game. So yeah, that's it for this footnote, and